In this video, we're going to talk about differentiation, which is the process of finding a derivative. Last time we talked about slope of tangent lines. So if you're given a function and a particular point on that function, this limit right here is the definition of the slope of the tangent line. Unless the function is itself a straight line, this slope of a tangent line is going to be different for different points on the curve. So we want to keep track of all those different slopes, and so we're going to define a new function. This new function is called the derivative of f. So in other words, if we have a function f, the derivative of the function, which is denoted one of two ways, either f prime, this guy right here, f prime of x, is the derivative of f at x, or this thing right here, this d over dx, this is not a fraction, that's a special notation, it stands for derivative. The derivative with respect to x of the function f. This is a new function, f prime, or d over dx of f. That function gives the slope of the tangent line for the function f at x. So in other words, if we replace x sub 0 up here in our definition of slope of tangent line with just plain x, we get this formula right here for the derivative. F prime of x, or the derivative of f at x, is the limit as h approaches 0 of this difference quotient, which is why you, in pre-calculus, you should have talked about this difference quotient for various kind of functions and used algebra to simplify it, things like that. Notice the slope of the tangent line is also the instantaneous rate of change of the function. So you can think of f prime, the derivative, as giving the rate of change of f. This is one of the main ideas of calculus, is rate of change. So if you have a function, maybe f is position of some object, the rate of change would be the velocity of that object. We'll see some examples of that later. So in this lab, we're going to talk about using Sage to calculate derivatives. That process is called differentiation, and we're going to look at some graphs of derivative functions to see what that tells us. So let's start with calculating the derivative function. So to calculate the derivative of a function in Sage, there's a command. It's called derivative. The derivative command takes two arguments, the name of the function or an expression for the function, and then second, the variable with respect to which the derivative is going to be calculated. Most of the time for us, that's x. Sometimes it's t, especially if we're dealing with time. It could be any variable, but usually we're using x. So in this example, I have a function f of x equals x squared. I want to find its derivative. I could do that using limits, like we did before. So here's the definition of the derivative, the limit of the difference quotient as h goes to 0. And we get the answer 2x. So this is another function. The derivative of the function f is another function. Instead of using limits, that's sort of the long way, we could use the derivative command. So here it is. You type out the word derivative and then parentheses. Here is the function we're taking the derivative of. That's the rule of the function f. And then a comma. And then x is the variable we're taking the derivative with respect to. And we get the same answer. Now you can also use a function name in the derivative command. So if you have previously defined the function f, then you can just put f here in the derivative command and it will give you the same thing, of course. So whichever way you do it, whether the limit or the derivative command, you get that the derivative f prime is 2 times x. So if you want the slope of the x squared function at any particular point, you just simply multiply the x value by 2, and that gives you the slope on the parabola. Here's a second example of a little more complicated function. So first I defined the function g, then I took the derivative of g with respect to the variable x. This is the messy answer, which is kind of hard to read, so I use the show command here. Remember, underscore refers to the last thing that came out. The last thing to come out was this messy derivative. So here is the answer in a little bit nicer format. Okay, so far we've calculated the derivative function as a function, just in general with the variable x. If you want the slope at a particular x value, x equals 10 or x equals -1, then you need to do a little bit extra work, another step. And there's two ways in Sage to get the value of the derivative at a particular point. And one is to give the derivative function a name, and now that you have the derivative function, just use that name to plug in the particular value. The second way is to add, after the derivative command, these parentheses, and then x equals, or whatever your variable is, here I'll use x equals whatever particular value you're trying to plug in. That will substitute in to the derivative. So let me show you both those ways with this example. So we'll go back to f of x equals x squared, and we saw that the derivative of this up above is just 2 times x. So if I want f prime of 3, that's asking for the slope of this x squared function when x equals 3. So the slope is 2 times x, so in this case when x equals 3, the slope should be 2 times 3 is 6. And we'll do that here. So, sorry, the answer, no output shows up from this. So here's method 1, define the function, and here we're defining the derivative of f. So here's the derivative of f, and I'm giving it a name. I call it df. And I do that because Sage doesn't allow f prime. The apostrophe to make the prime is a reserved symbol for other things. So I can't call it f prime. I could say f and then type out the word prime, but that's too long. So I use df. D for derivative. So for me, df is the derivative of f. You can call this whatever you want. So I now have defined this function df to be the derivative of f. And again, no output comes out because I'm just making a definition here. Now that I have my derivative function defined, I can plug in x equals 3 using normal function notation. So df of 3 is f prime of 3, and the answer is 6. Here's the second way. So in the second way, you put the derivative command, just like before. That produces the answer 2 times x. And then this little business with parentheses says, now substitute in that expression 2 times x, substitute x equals 3. And you get 6. So it calculates this just like above, and then it substitutes afterwards. Be careful, this x equals 3 in parentheses needs to come after the derivative command. So right here, the derivative command begins, derivative parentheses, all this stuff goes into the derivative command, and here the derivative command ends. Don't put this x equals 3 inside the derivative command. There's no place for this 3 in there. You put a 3 inside there, you get something else. We'll see later on what that is. All right, here's another example with the function g, the same g that I had up above. I want to do g prime of 5. So method 1, give the derivative a name. I call it dg for derivative of g. There's nothing sacred about that name. You can call it whatever you want. Name it after yourself if you want to. But give it a name, and then use that name to plug in the x equals 5. And this is the answer we get. If that answer is kind of messy, you might want to use the capital N command to convert to decimal. So here it is. I put the capital N command on the derivative of g at 5, and I get this decimal, very small number there. Notice the scientific notation. This E thing, remember, is scientific notation. This says negative 1.63 times 10 to the minus 8. That's what we got down here. And so this is actually a very small number. Second method, add the particular value of the derivative after the derivative command, or add the particular value of x, I should say. So here it is, here's the derivative command, and then here's the particular value of x afterwards, x equals 5. And we get the same answer as we got for method 1. If I want the value of the derivative at some other x value, so here is x equals minus 3, then if you're using method 1, you already have dg, so it's just a matter of using it again. And then if you want to convert to decimal, use the n command. You don't have to recompute the derivative. If you're using method 2, you have to compute the derivative over again, and then plug in the x equals minus 3 afterwards. So either one will give you the same answer. If you have several different particular values to calculate, then method 1 is going to be more efficient. It only does the derivative once, and then you can plug in as many numbers as you want after that. Method 2, you're going to have to plug in, you're going to calculate the derivative over and over and over again, which may take a little time depending on the function. But if you're just doing it once, then there's actually less typing here. though not much less. I personally prefer method 1. I think it shows a little more clearly what exactly is going on, but you can do this if you prefer method 2. That's fine with me. Nothing sacred about the variable x, so you can do derivatives with functions where other variables are involved. You might have another variable for the input, so maybe it's f of w instead of f of x. You can also have other variables involved in the definition of the function, like here in this capital F, I have ax squared plus bx plus c, and the idea is that a, b, and c are just constants, and we're trying to find the derivative of this sort of general parabola where the a, b, and c are unspecified. The fact that this function is called f of x tells us that x is the input variable, and that's the variable we're going to take the derivative with respect to, and we'll just assume that a, b, and c are constants. So here it is. I defined a, b, and c to be variables, so those are just empty constants. And here's the capital F I defined. I did the derivative of that, and here's the answer. I used show to make it a little nicer. And you can see that the a and the b show up as part of the answer, so those are involved there. And if you put particular numbers in here, a is 3 and b is 9 and c is 8, then you put them in there, you would get the right derivative. If we take the derivative with respect to a, b, or c, we will get a different answer. It's a little awkward in this case because, of course, f is written as a function of x. And this is not a normal calculus 1 question, but I'm doing this example just to show you that Sage can take the derivative with respect to other variables. So here's what happens if you put the capital F function and take the derivative with respect to a. You get just x squared. Try to twist your mind around this. If a is the variable, then you got variable times a number. Okay, so if a is the variable, then x is a constant. So x squared is a constant. So this is the variable a times a constant plus all of this is constants. So as far as a is concerned, if a is the variable, this is actually a straight line with slope x squared and y-intercept bx plus c. If that's confusing, then don't think about it too long. But anyway, this is showing us that the derivative of f, if a is the variable, is x squared. It's a line with slope x squared. The derivative with respect to b is just x. It's a line with slope x. And the derivative, if c is the variable, is just 1. It's a line with slope 1. Everything else is constant. Okay, here's an applied example where we do velocity. So if your original function is a position function and you want to know the rate of change of position with respect to time, that's called velocity. Then velocity is the derivative of the position function. So here's an example. This p function, p of t, gives the position in feet of this object that's moving in a straight line where t is measured in minutes. And the question is, how fast is the object traveling at t equals 10 minutes? So what's the instantaneous velocity at 10 minutes? So I define the function p. There, that's my position. The velocity is the derivative of p, so here's the derivative of p. I'm going to call that v of t because v for velocity, though you can call it whatever you want. The question asked me for the velocity at 10 minutes, so I'm going to plug in 10 to the velocity function. And Sage tells me the answer is negative 20, so the object's velocity is negative 20 feet per minute. You could use method 2 if you want, though if you use method 2, make sure you use t equals 10 and not x equals 10, so the variable here is t. So if you're going to use method 2, make sure the variable you're substituting matches the variable in your function. And you get the same answer, of course. All right, higher order derivatives. So the derivative function, f prime, might have slopes of its own. And so if you want the slopes of f prime, you're looking at the derivative of f prime. The derivative of f prime is called the second derivative of f. And rather than writing it like this, where you got f prime prime, we just kind of merge that together and write 2 primes. This is called f double prime. So the second derivative of f is denoted f double prime, or in the Leibniz notation with the d's, it goes d, it looks like d squared, but it's not a squared, it's just a that's the notation for the second derivative. So you should read this set of symbols as the second derivative of f. And you can read this one as f double prime. And then, of course, f double prime has slopes of its own. If you take the derivative of f double prime, then you get what's called the third derivative of f, which we denote like this, f triple prime, so f with 3 primes. Or in the other notation, this is the third derivative. D for derivative, 3 for the third derivative, and then the x here indicates that the derivative is with respect to x. After the third derivative, I stop using prime. Some people will do quadruple prime, and they'll actually have 4 tick marks. But after 3, I think it starts getting confusing. You actually have to count how many primes there are. And so instead, this is the alternative notation when you have too many primes, f, and then in parentheses, a 4. So this stands for the fourth derivative of f, which is the derivative of f triple prime. Or this is the other notation for the fourth derivative of f. The 10th derivative would have this notation, f with this little superscript 10 in parentheses. Don't forget those parentheses. That's what tells you that this is the 10th derivative as opposed to the 10th power of f. Or you can use this d over dx notation with the 10. To do this in Sage, we simply add one more argument to the derivative command. So using the same little f, little g, and capital F from the examples above, this is the second derivative. You put a comma 2 and you get the second derivative. So function f, variable x, and then this 2 means second derivative. Common mistake that students make is think that this 2 means calculate f prime of 2. This is not f prime of 2. This is f double prime of x, which happens to be a number. Here it is with g. So the derivative of g, comma x, x is the variable, and then comma 2, that's what does the second derivative. And this is the second derivative of g, which is a pretty complicated thing. Here is the second derivative of capital F 2 times a. Here's a random assortment of higher order derivatives. So here's a third derivative. You put comma 3. In this one, the third derivative is 0. Notice that once you hit 0, if the third derivative is 0, not just at one point, but the 0 function, it's 0 everywhere, then of course the fourth derivative is going to be 0, and the fifth derivative will be 0. Once you hit 0, you're going to be 0 from there on, because the derivative of 0 is 0. Now that doesn't happen in, why is this looking weird? Sorry about that, we had a little pause there to fix this display issue, but there's the fifth derivative of g, so this comma 5 says fifth derivative. Now this g function never ends up at 0, it gets worse and worse. The more derivatives you take, the worse this function becomes. Go back up and look at g prime and g double prime. They were not quite as complicated. Here, fifth derivative is even more complicated. The fourth derivative of capital F is 0. Now if you want a particular value of one of these higher order derivatives, you have the two different methods we had with the first derivative. So if I want the 10th derivative of the function g evaluated at x equals 7, that's what this says, then here's method 1, calculate the derivative function. This is the 10th derivative. Give it a name. I call it d10g for 10th derivative, d for derivative and 10 for 10th derivative. Again, the name is not important, just give it a name. And now use that name, plug in x equals 7, and this is the answer that comes out. If you want to convert to decimal, here's the thing to convert to decimal. Again, notice the scientific notation there. This is a small number, just barely above 0. If you like method 2, you can use that. So here's the 10th derivative. That calculates the 10th derivative function, and then this substitutes x equals 7 into the answer. All right, we did the applied example of velocity, which is the first derivative of position. Acceleration, by definition, is the rate of change of velocity. So in other words, acceleration is the second derivative of position. So you can find acceleration in two ways, either by doing the velocity first and then taking the derivative of velocity, or you can just start with position and take the second derivative directly. Okay, so here's the position function that we had above. We found the velocity of this before. Now I want the acceleration of this object after 10 minutes. So I define my function p. I took the derivative, the second derivative of p, which is acceleration. So I called it a for acceleration. And once I had that function, I plugged in the t equals 10 minutes, and I got -6. So the acceleration is -6 feet per minute, which normally we write as feet per minute squared. All right, I want to talk a little bit about what the graph of the derivative tells you about the graph of the function, how those are related. So I'm going to start with a simple example of the little f is x squared and its derivative. So remember we did this before up above. We saw that the derivative of x squared is 2x. So here's the graph, the derivative of the original f, x squared in blue, and the graph of f prime, the derivative in red, that's 2x. And here's some of the things I want you to notice about that picture. When the original function is increasing, the derivative is positive. So here, starting at 0 and going off to infinity, the blue curve is going up. That's increasing. And that increasing portion of the blue curve corresponds to the red part being positive, above the x-axis. Over here, this function is decreasing. The blue guy is going down from negative infinity until x equals 0. The blue one is decreasing. That corresponds to the red line. The derivative is negative, below the x-axis. The y values here for the red line are negative y values, below the x-axis. So negative function values in the derivative corresponds to decreasing function values in the original function. Okay, notice that the derivative is actually increasing everywhere. So the derivative increasing does not correspond to the function increasing or decreasing. That's not the connection. The connection is between derivative positive, increasing function over here, derivative negative, decreasing function over there. And finally, at the local minimum, x equals 0, the derivative is 0. The derivative equals 0, and the function changes direction, changes from decreasing to increasing, which produces a local minimum right there. All right, example 13. Here's little g. This is a little more complicated function, but we see the same relationship when the function in blue is increasing. So like right here, from x equals 0 until x is 1 point something, till we hit this peak. This little chunk right here, we see the function is increasing. And that corresponds to the derivative being positive. The derivative in red is above the x-axis. The function values of the derivative, the y values of the derivative, are positive when the blue part is going up. Over here, the function is also increasing on this side. The function g is increasing from this local minimum, the trough, and it's actually increasing all the way to this peak. This whole way it's increasing. But I'm just looking at this little portion right here. The function is increasing, going up. The derivative is positive. And again, there's no relationship to the function being positive or negative. Notice this function is negative here and then positive here. The function actually changes sign. Negative y values change to positive y values. The derivative, though, is positive the whole time. So there's no connection between positive function and positive derivative. The connection is between increasing function, positive derivative, and then here, from this peak on, the function is going down. So in this portion, the blue is decreasing, and the function is negative. The derivative, sorry, is negative. The red is negative, negative y values below the x-axis, negative derivative, decreasing function. Same thing over here. The function is going down until it hits the bottom down here. So right in this portion, the blue guy is going down, the red guy is negative below the x-axis. All right, and that's what it says here. At the local minimum or local maximum, the derivative is 0. So here's a local maximum for g. G prime is 0. Here's a local minimum. for g, g prime is 0. Now we can also see some things about concave up and concave down. When the function g is concave up, the derivative is increasing. When the function g is concave down, the derivative is decreasing. Okay, so here's a portion of concave down for g. The blue is concave down. If you wrap your hand around the blue curve right here between, say, like 1 and 2, your palm will point down. That's concave down. And in that concave down portion of g, g prime is going downward, decreasing. And here's a concave up part for the blue, and the red is going up, increasing g prime, concave up g. And at an inflection point where there's a change from concave up to concave down, like for example right around in here, this little part concave up, this part is concave down, right in the middle somewhere in here it changes from concave up to concave down. That's called an inflection point. The inflection point on the blue curve, g, corresponds to this local extreme value for g prime. This local max gives us an inflection point. Same thing, this local min down here corresponds to this inflection point there. Changes from concave down to concave up. So when there's an inflection point, g prime has a local max or min. We're going to do a lot more of this type of stuff later on in the semester. This is just a preview of coming attractions. Our topic last time was tangent lines, and we use limits to find the slopes of tangent lines. Now that we have the derivative function, we don't have to use limits anymore. That's all built into the derivative. So in general, here's the formula for a tangent line for the function f. At the particular x value, x equals x sub 0. It's the value of the function plus the slope times x minus your particular x value. This is just point slope form of a line, except now the y value, the particular y value, comes from the function. F of x sub 0 is your y value. F prime of x sub 0 is the slope. F prime, by definition, gives you the slope of f. So instead of having a limit here, we can just have f prime. That's the slope. All right, let's use little g from above. At the particular x value, x equals 2. And so the equation of your tangent line would look like this. Y equals the y value, g of 2, plus the slope, g prime of 2, times x minus the x value, which is 2. In Sage, we can do it this way. First define the function g, then define the derivative function. That's what's going to give us our slope. And then we type in the tangent line equation here, just like it is up above. I gave it the name TL for tangent line, and it's just this formula with dg in place of g prime because I called it dg. I use the show command just to show the answer here. So here's the here's an equation for the tangent line of little g at x equals 2. And here's a plot of both of them. So the blue curve is g, the red is the tangent line. I also put a dot right here at the point of tangency just so we could see where it is. And if I were to zoom in on this graph, which I won't do, you would see that the blue and the red would be very, very close together, close to x equals 2. One last example and we'll be done. An applied example to population growth. So suppose that capital P of t is the population of whatever at time t. The derivative p prime gives you the rate of change of the population, how fast that population is increasing or decreasing, as the case may be. So here's a specific example. Suppose you live in a city called Sageville. The population of Sageville, t years after it was founded, is given by this complicated equation. This is called a logistic model for population growth. You may or may not have covered that in pre-calculus. If you want to know at what rate is the population increasing 100 years after its founding, the rate of increase is the derivative. So this question is asking you to calculate p prime of 100. So here I'll use method 1. So I define the function p. You gotta be really careful with parentheses here. There need to be parentheses around the bottom of the fraction to get the order of operations right, there needs to be parentheses around this exponent right here, the negative 0.1 times t. That's all the power of e, and so you need those parentheses there, so all of that is in the power. I'll call my derivative dp, so this is my p prime, and now I just need to plug in the t equals 100, and I get 6.99. That means the population is growing at a rate of approximately 7 persons per year, 100 years after the founding of Sageville. Now, a common mistake here, when I've given this question to students, they'll say that the population is increasing at a rate of 7%. This is not a percentage. This is 7 persons per year. The units of the derivative is the units of the function, the y values, per the units of the input, the t value here. So it's persons per year. This is not 7%. The 7 persons is actually 0.2% of the population at the time. So it's make sure you get your units right. Don't insert percentages where they don't belong. I want a formula for the tangent line of this population function at t equals 100. I'm going to go ahead and graph them. So here it is. I already defined the function p up above. I defined the derivative dp up above. So here's the formula for the tangent line. It's y value plus the slope times x minus the x value. And then I'm just going to plot the p, and I'm going to add a plot of the tangent line, and I'm going to add a point at the point of tangency just for fun. So here's the graph of the population. So you can see that it grows really quickly at the beginning. This is sort of exponential growth at the beginning. And then it kind of tapers off, and it reaches what's called the carrying capacity. As the population, or as the time gets bigger and bigger, the population levels out. The Sageville can't accommodate any more people. It's reached the boundaries of how many people it can have. That's what the logistic model looks like. And you can see this thing, this tangent line, closely follows the curve here, close to time at 100. All right, p double prime of 100. What does that mean? So remember, second derivative, p double prime means second derivative. Here's one way to calculate it. Remember, comma 2 does second derivative. I gave it the name d2p for our second derivative of p. I plugged in the 100. This is what came out. So p double prime is negative 0.67. The units here are persons per year, or persons per year squared. So in other words, it means that the rate of increase of the population, that's the derivative, the rate of increase is going down by 0.67 persons per year every year. So around the time t equals 100, every year the rate of increase is getting a little bit smaller. So it's still increasing, but it's not increasing quite as fast. This doesn't, the population never decreases. According to this model, if you look at the graph, the population never goes down. The population is always increasing, but it's not increasing as fast. Down here, it's increasing very quickly. Up here, it's increasing slowly, and the rate of increase is falling. That's what this number is telling us.